This is going to be a discussion about the concept of continuity. Now that we've had a conversation about limits and what they are and how we calculate them and how we deal with them, we want to also lay some groundwork on the idea of continuity, because most of the theorems that we're going to deal with in this course have a requirement that the function you're dealing with be continuous. So since it's going to show up so many times, we want to have a pretty deep conversation about what we mean by continuity, a little bit deeper than you would get in a college algebra or a pre-calculus class. In those classes, if we want to discuss continuity, what we say is, well, if you can draw the graph of your function without picking up your pencil, then it's a continuous function. But in calculus, we want to get a little bit deeper than that. So let's start with the actual mathematical definition of continuity. And it says that a function f is considered to be continuous at a specific number a if the limit as x approaches that a of the function is equal to f of a, is equal to what you get when you plug a into that function. That is a deceptively short definition. That's a lot of information in a very small package. That actually has three things to say to us. The first one is that f of a is defined. If you're going to have a limit, and that limit has to be equal to f of a, that implies that f of a exists. It's defined. And what that tells us is that a is in the domain of f. So when you discuss continuity, you have a lot of talk about domain. They are very, very closely related. So in order to be continuous at a number, the number has to be in the domain of the function. The second thing that tells us is once you know that a is in the domain of that function, the limit as x approaches that a on the function has to exist. So we've paired up two ideas, domains and limits. And this is actually why we don't define continuity this precisely until we get to a calculus class, because the definition of continuity involves a limit. So the limit has to exist. In other words, the left-hand limit as x approaches a has to equal the right-hand limit as x approaches a. If you can have those two things, there's a third condition that has to be met. Once you know that a is in the domain, and you find f of a, and you know that the limit as x approaches a on the function exists, in order for the function to be continuous at that a, the limit and the evaluation of the function, both at a, have to be equal to one another. So if any of those conditions are not met, what we say is that the function f is discontinuous at a, or it has a discontinuity at a. That's really just a difference between discontinuity is a noun and discontinuous is an adjective. So it's either discontinuous at a or it has a discontinuity at a. There are three kinds of discontinuities. The first one is called a removable discontinuity. And sometimes that'll be referred to as a hole. You've probably seen these in your pre-calculus or college algebra classes. So the limit exists as x approaches a, meaning it meets that second condition. The limit as x approaches a from the left equals the limit as x approaches a from the right on the function. But either the limit is not the same as what you get when you plug a into the function, or f of a may not exist at all. It may be undefined at a. So if you run into that situation, you're looking at a removable discontinuity. These, as the name kind of implies, you can actually remove the discontinuity simply by redefining one point on the function. It requires a piecewise definition for the function. You have to basically turn your function into a piecewise function. But it is a one-point change to change it from discontinuous to continuous. So you've run into these before when you're dealing with rational functions, in which a denominator becomes 1 after a cancellation. So for example, we've seen basically in your pre-calc classes, you ran into questions like this. If you have f of x equals x minus 2 times x plus 1, over x plus 1 times, I don't know, x minus 3 kind of thing. And you are asked where are the vertical asymptotes of this function if you were trying to graph it. Well, if you remember, when you cross out the x plus 1s, you are in fact going to pick up a vertical asymptote at x equals 3. But what you're not going to pick up a vertical asymptote at x equals negative 1. This function is equal to x minus 2 over x minus 3, which is where you're going to get your vertical asymptote at 3. However, it's got the added understanding that x cannot be equal to negative 1. So you'll get a vertical asymptote at x equals 3, but at x equals negative 1, all you get is a hole in your graph, which we now know is called a removable discontinuity. So what these looked like when you were dealing with them in your pre-calc classes, this is, that's supposed to be a circle. This is a removable discontinuity if you look at it graphically, but also if I fill the hole somewhere else, it's still a removable discontinuity. So notice in both of these cases, if this is my a value, the limit as x approaches a from the left and the right are the same. The limit exists, but in this case, f of a is undefined. And in this case, f of a, it is defined, but it's not going to be the same as the limit value at that a. The second kind of discontinuity we'll run into is a jump discontinuity. And as the name implies, there's literally a jump in your graph. So if you're looking at a graphical representation of this, this would be something along these lines. It doesn't have to be open circle and closed circle in that order. But if you notice, if this is where my a is located, we have a jump discontinuity here. Notice that the limit as x approaches a from the left and the limit as x approaches a from the right will give me two different values. So the limit on as x approaches a for jump discontinuities does not exist. It's one of the ways you can pretty quickly pick those up. A may also be out of the domain. In this case, the one I've drawn, a is in the domain. You can plug a into this function and you will get whatever y value this one gives you, but you could also run into a situation where both of these are open circles. This is still a jump discontinuity, but if this is where a is located, it's undefined at a. Could be either though. These cannot be removed by redefining a specific point. Step functions are an example of a jump discontinuity. When you use a cell phone plan, if you take a look at the graph of the time compared to how much money you're paying, if I were to break this up into minutes, say 1, 2, 3, and just for ease of this example, let's say it's $1 per minute. Just to make my life easy. So for example, if you talk for 30 seconds, do you only pay for 30 seconds? Well, no. As soon as you talk for 30 seconds and hang up your phone, that's considered a minute. So from the beginning, you are going to pay, again, assuming it's $1 per minute, as soon as you start talking on this phone, you're going to start paying $1 all the way up until 1 minute. And then the moment you go over 1 minute, meaning you talk for 1 minute and 1 second, you are now considered to be up into the next rank. You will pay for 2 minutes at that point. So these step functions tend to look like this. So cell phone plans are usually the most common example of a step function. They are by no means the only example. The third type of discontinuity we'll see is an infinite discontinuity. So for these, they primarily occur at vertical asymptotes. And what you'll see is that when you look at the limit, because remember we're talking about continuity again, we will be evaluating the function at a and looking at the limit as x approaches a. Well, when you look at those limits, what's going to happen is either your left limit or your right limit, or both, are going to yield an infinity or a negative infinity. As soon as you see that, you're looking at an infinite discontinuity. So any function with a vertical asymptote, this is going to happen. So rational functions, logarithmic functions, etc. So let's take a look at this particular graph to give us kind of a visual representation of what we're looking at. If we were in a pre-calculus class, I would simply say, hey, look, you can tell you have to pick up your pencil at -3. There's a discontinuity. You have to, again, pick up your pencil at 1. That's what the dashed vertical line is intending to imply. So you have a discontinuity at -1, and then you have another discontinuity at 2. But since we're in a calculus class, we're going to talk about what kind of discontinuity we're looking at. So if you notice at x equals -3, the limit from the left is not the same as the limit from the right at -3. That tells us that we have a jump discontinuity. We continue on, and what we notice is that at x equals -1, this seems to increase without bound, and that vertical dash line is intending to imply that there's a vertical asymptote there. So that tells us that we have an infinite discontinuity at x equals -1. Okay, then we keep looking, and here at x equals 2, there is a hole in our graph. The limit as x approaches 2 from the left and the limit as x approaches 2 from the right are equal. They both appear to be -1/2. However, f of 2 seems to be -1. So while the limit exists, it's not the same as what you get when you plug 2 into the function. So that means that at x equals 2, we have a removable discontinuity. So notice for each of these, I've given you 2 pieces of information: where the discontinuity is occurring and what kind of discontinuity we're looking at. So this is what it looks like to identify discontinuities from a graph. But what we also want to be able to do is identify discontinuities simply by looking at the equation of a function. So we're going to determine the points at which the function is discontinuous and state the type of discontinuity, which is what we did for the graph as well. But we're going to do it given the equation. So let's start with f of x equals x squared minus x minus 2 over x minus 2. And since we're discussing discontinuities, remember that the definition of continuity is that the limit as x approaches a on f of x has to be equal to f of a. That's our definition. Now, I didn't give you an a for this particular function. We haven't necessarily been told where we should be looking, so we're going to have to decide that for ourselves. Well, remember, the first piece of information that this implies is that a has to be in the domain of the function. So if you're looking to identify where a function is discontinuous, you want to take a close look at its domain. Because this is a rational function, we're going to want to look wherever the denominator is equal to 0. We look at x equals 2. This is where we will have a discontinuity. What we need to do is determine what kind of discontinuity it's going to be. Don't jump to any conclusions too quickly. We want to take a look at 2 pieces of information to determine that. We need to know f of 2, and we need to look at the limit as x approaches 2. Okay, so f of 2, we just said it's out of the domain. So f of 2 is undefined. Okay. In order to calculate the overall limit as x approaches 2, we're going to have to verify that the left and the right-hand limit are the same. So let's start by looking at the limit as x approaches 2 from the left on the function. Notice the numerator is a quadratic, which makes me highly suspicious that it might actually factor, and it turns out it does in fact factor. This factors to x plus 1 times x minus 2. So what you're going to notice is that those x minus 2's are indeed going to cancel. So this is actually going to turn into the limit as x approaches 2 from the left on the polynomial x plus 1. Now remember, polynomials are eligible for direct substitution, so we're going to get 2 plus 1, also known as 3. If you look at the limit as x approaches 2 from the right as well, you're also going to get the same kind of cancellation. So you're going to end up canceling the x minus 2's and doing direct substitution again and getting 3, which says that that limit overall does in fact exist. The limit as x approaches 2 on x squared minus x minus 2 over x minus 2 is in fact equal to 3. So now that we have the limit and we have f of 2, we need to do a comparison between these 2 pieces of information. The limit as x approaches 2 is equal to 3, but f of 2 is undefined. So while the limit as x approaches 2 exists, it's not the same as what we get when we plug 2 into the function. That tells me that we have a removable discontinuity at x equals 2. Okay, let's take a look at this one. We have f of x equals 1 over x squared if x isn't equal to 0, and 1 if x is equal to 0. So again, the first thing I need to identify is where I should be looking for my discontinuities. I actually have two places I want to check. Because this is a piecewise function, I need to check the domain of each piece. The bottom piece I'm not worried about. The bottom piece is f of x, or y, equals 1. That's just a constant function. That has no domain problems. The top piece, however, is f of x equals 1 over x squared. And since that's a rational function, that indicates I need to examine wherever the denominator is equal to 0. Well, that happens at x equals 0. So I should be looking at x equals 0. Now, the other thing I need to keep an eye on for discontinuities is anywhere that my piecewise function changes from one piece to another. Because as we saw with limits, when you look at a piecewise function, a couple of things can happen. You can have a piecewise function that you're graphing and it stops and switches to another piece, and maybe the other piece ends up here, or other times you'll graph your piecewise function and you'll start to draw it and you'll have an open circle, and then when you draw the other piece it happens to match up. So it just depends on which of those two you're going to get. So that tells me that I would need to examine wherever the piecewise function switches from one piece to another. Well, that happens to also be at x equals 0, so I'm already looking there. So we need the same two pieces of information. I need f of 0, and I will also need the limit as x approaches 0. So f of 0, this is a piecewise defined function. So in which of the two pieces can I plug in 0, if any? Well, the first piece you can use only if x isn't 0, so it's definitely not there, and x equals 0 on the second piece. So you can absolutely plug 0 into the piecewise function. The output is 1. So f of 0 is 1. So we now need to look at the limit as x approaches 0. So again, in order to verify that the limit overall exists, I have to look at both the left and the right-hand limits. So if we look at the left limit first, that's the limit as x approaches 0 from the left. I have to decide which of the two pieces to use. This one's a little bit different than the examples we did in the previous section because this doesn't have greater thans and less thans, but it does have equal to and not equal to. And remember, limits are about what happens near a value, not at the value. So since we're coming at 0 from the left, we just need to pick the piece that isn't exactly equal to 0. That's the top piece. So this is the limit as x approaches 0 from the left on 1 over x squared. Now, if you recall, we did this one in the previous section. You can't use direct substitution on this because it will give you a 0 in your denominator, but you can either think of this graphically, that's your smokestack graph, or you can think of it as it's a constant 1 divided by a number that approaches 0, meaning it's getting smaller and smaller and smaller. So when you take a constant divided by something getting very, very small, the fraction overall gets very, very large. And because this is x squared and everything's going to come out positive, it gets positively large. This goes to infinity. Now, as soon as you see that, we now know this is an infinite discontinuity. But just for the sake of rigor, I'm going to go ahead and write down the right-hand limit as well. We have the limit as x approaches 0 from the right on this function. We would also use the same piece of the piecewise function. We would still be looking at 1 over x squared to equal infinity, which means that the limit overall as x approaches 0 on the function equals infinity. So once we have those two pieces of information, we compare f of 0 to the limit as x approaches 0. They are not the same, so we do have a discontinuity, and the limit was equal to infinity, which means we have an infinite discontinuity at x equals 0. Okay, let's take a look at another one. If we look at the function f of x equals x squared minus x minus 1 over x minus 2 if x doesn't equal 2, and f of x equals 1 if x is equal to 2. So the top piece should look very familiar. That's out of example 1. So because we've already done this, I think I can safely recall that that is x plus 1 times x minus 2 over x minus 2. That's from the first example. So we need to determine where we think the discontinuities are going to occur. So just like in example 2, I need to look at the domain of each piece. The domain of the top piece, 2, is out of its domain. The bottom piece is a constant, so that's fine. So 2 is the place that I think I need to examine. That also happens to be where I'm switching from one piece of my piecewise function to the other. So we are suspicious. We're going to have a discontinuity at x equals 2. So I need the same two pieces of information. I need f of 2, and I need the limit as x approaches 2. I need to see if these are the same. All right, so f of 2 says plug 2 into your function. That does not occur in the top piece, that occurs in the bottom piece. So f of 2 is 1. The limit as x approaches 2, again, in order to find the overall limit, I need to split this and look at the left-hand limit and the right-hand limit. Just like example 2, in my piecewise function, if x isn't 2, meaning you're coming at 2 from either the left or the right, we are in fact going to go ahead and use that top piece in both cases, for both the left-hand limit and the right-hand limit. We've already done that in example 1, so I'm not going to rewrite everything we did. I'm just going to write down our conclusions that we came to. From example 1, we know that the limit as x approached 2 from the left on f of x was 3. The limit as x approached 2 from the right on the function was equal to 3, which said that the limit overall on this function is also equal to 3. Once I have f of 2 and the limit as x approaches 2, I compare these two values. So the limit exists, f of 2 exists. However, they are not the same value. So we do have a discontinuity at x equals 2, but specifically, what kind of discontinuity do we have? This one is a removable discontinuity. So we have a removable discontinuity at x equals 2. Okay, let's look at one more. We're going to look at the function f of x equals 0 if x is less than 0, and 1 if x is greater than or equal to 0. This is actually what is sometimes referred to as a Heaviside function. It's a piecewise function that only returns one of two values, either a 0 or a 1. So basically, in either electrical engineers will use this, computer engineers will use this. This function acts as an on-off switch. If you like the input, so in this case it would be positive, turn your switch on. If you don't like the input, turn your switch off. So this is actually pretty heavily used in engineering. But what we want to do is examine the discontinuities. Both pieces of this function are constant, meaning their domain is all real numbers. So in order to determine where I think I'm going to have a discontinuity, domain's not an issue. So where I need to look is where this switches from one piece of the piecewise function to the other, which happens to occur at x equals 0. So we're going to look at x equals 0. Same two pieces of information. I need f of 0, and I need the limit as x approaches 0, and I'm going to compare these two values. So f of 0, we're looking for which piece of the function we should use if x is exactly equal to 0. That's going to be our bottom piece. So f of 0 for this function is 1. In order to find the limit as x approaches 0 overall, I need to look at the left limit and the right limit and see if they match. So the limit as x approaches 0 from the left. Now we're back to the greater thans and less thans. So we're coming at 0 from numbers smaller than 0. Which of the two pieces of the piecewise function should we use? That's going to be the top piece. So we're going to look at the limit as x approaches 0 from the left on 0. Well, that's a constant, so the limit of the constant is the constant, that is 0. If we look at the limit as x approaches 0 from the right on this function, you're coming at 0 from numbers larger than 0. That's the bottom piece. So for that one, we would take the limit as x approaches 0 from the right on 1, which is also the limit of a constant, which is itself. Notice the left-hand limit and the right-hand limit do not agree. So therefore, the limit as x approaches 0 overall on this function does not exist. So we do a comparison. This time it's the limit that does not exist as x approaches 0. You can plug 0 into the function, but since the limit doesn't exist, that tells us that we have what kind of discontinuity? That's going to be a jump discontinuity. So we have a jump discontinuity at x equals 0. So since we have limits from the left side and limits from the right side, and since the definition of continuity contains a limit, it shouldn't be that big a surprise that we also have continuity from the right and continuity from the left. So when you have a function that is discontinuous at a certain value a, while it's discontinuous there, it could be just continuous from the right at a or just continuous from the left at a. So let's see what we mean by that. A function f is continuous from the right at a number a if, when you take the limit as x approaches a from the right on the function, you get the same thing as f of a. You get what you get when you plug a into the function. A function is continuous from the left at a number a if the limit as x approaches a from the left on the function equals f of a. Not really surprising that right-hand and left-hand continuity depend on right-hand limits and left-hand limits. A function that's discontinuous at a can be continuous from either the left or from the right. That doesn't mean it has to be. It can also be neither continuous from the left nor the right. So let's take a look at some examples of what that looks like. We're going to determine the points at which the function is discontinuous. We've actually already done that for these examples. And state whether the function is continuous from the left, right, or neither there. Now I've chosen ones that we've already worked through. This is the same as example number 1 from just find out what kind of discontinuity you're looking at. Because while this is an additional question to look at, we've actually done all of the work that we need to be able to answer this. So if you recall, we actually already determined that this has a discontinuity at x equals 2 and that it was a removable discontinuity. So what we want to do is determine at x equals 2, is it continuous from the left, the right, or neither? So we need the same 3 pieces of information that we used before. We need f of 2, we need the limit as x approaches 2 from the left, and we need the limit as x approaches 2 from the right. So these are the 3 pieces of information we already had. So in order for the function to be continuous from the left, what we would need is the limit from the left to be the same as f of 2. Is that the case? No, so it's not continuous from the left. If you want this to be continuous from the right, what we would need is the right-hand limit to be the same as f of 2. Is that the case? No. So this one is continuous neither from the left nor from the right. Let's look at another one. This is the same as example number 2 that we just completed. Same 3 pieces of information that we need. Once we have f of 0 equal to 1, the limit as x approached 0 on the function was infinity, and the limit as x approached 0 from the right on the function was also infinity. To determine whether it's continuous from the left, we compare the left limit at 0 with f of 0. Are they the same? No, so it's not continuous from the left. If you want to determine continuity from the right, you compare the right-hand limit to f of 0. Are those the same? No, so this one is also neither continuous from the left, nor is it continuous from the right. If we look at the third example, same three pieces of information that we need. From the previous questions we were answering, we knew that f of 2 is 1, the limit as x approached 2 from the left on the function was 3, and the limit as x approached 2 from the right on the function was 3. Our conclusion was that this had a removable discontinuity at x equals 2. So at x equals 2, is this continuous from the left? Well, we need to compare the left limit to f of 2. Are they the same? No, so this is not continuous from the left. Is it continuous from the right? We need to compare the right limit to f of 2. Are those the same? No, so this is also neither continuous from the left nor from the right at x equals 2. I promise we'll get to one where that's not the case. Let's take a look at the Heaviside function that we examined. Remember the three pieces of information we had. We knew that f of 0 was 1, the limit as x approached 0 from the left on the function was 0, and the limit as x approached 0 from the right on the function was 1. Our conclusion was that this had a jump discontinuity at x equals 0. So, if we want to determine at x equals 0 if this is continuous from the left, we compare the left limit at 0 to f of 0. Are those the same? No, so this is not continuous from the left. If we want to check and see if this is continuous from the right, we compare the right limit at 0 to f of 0. Are those the same? Yes, now we've got it. So this particular function, while it is discontinuous at x equals 0, at x equals 0 it is continuous from the right. Okay, let's look at a new example. Here's a piecewise defined function. It does have three pieces to it. We're going to determine the points at which the function is discontinuous and state whether the function is continuous from the left, right, or neither there. We need to find where it's discontinuous, and then at those discontinuities determine is it continuous from the left, the right, or neither. So the first thing we want to do is figure out where we should be looking for these discontinuities. If you look at each piece of this piecewise function, this one's a quadratic, this one's linear, this one's a quadratic. So each piece is a polynomial. And remember that the domain of polynomials are all real numbers. So I don't have any places where I'm going to have domain issues for each piece. So I don't pick up any clues there. But this is a piecewise defined function, so I need to examine where we are switching from one piece to the other. Well, that's actually two places in this case. I need to examine x equals 0, and I need to examine x equals 2. So I have two places to look for discontinuities. So for each one of those, I need the same two pieces of information. I need f of 0, and I need the limit as x approaches 0 on the function. For 2, I need f of 2, and I need the limit as x approaches 2 on the function. Once I have those pieces of information, I'm going to be able to determine if it has a discontinuity. I'll also be able to tell what kind of discontinuity, and then whether it's continuous from the left, right, or neither there. So let's do that. For x equals 0. Okay. To find f of 0, we need to determine which piece we should be using to plug in 0 exactly. Well, the or equal to for 0 occurs in the first piece, so that's where we'll be plugging in 0. So f of 0 will be 1 plus 0 squared, also known as 1. We also need the limit as x approaches 0. To determine that, to find the overall limit, we need to look at the left-hand limit and the right-hand limit at 0. So as we come at 0 from the left, that means you're coming at 0 from numbers slightly smaller than 0. So which piece contains numbers slightly smaller than 0? That's also the first piece. So that will be the limit as x approaches 0 from the left on 1 plus x squared. Now because that is a polynomial, it is eligible for direct substitution, and that limit's going to be equal to 1. We want to next find the limit as x approaches 0 from the right on the function, and we need to figure out which piece to use in order to calculate this limit. Now you want to be just a little bit careful on this, because you are approaching 0 from the right, which means you're coming at 0 from numbers slightly larger than 0, but slightly larger than 0. If you look at this bottom piece, this is the piece you use if x is greater than 2. And while 2 is larger than 0, it is significantly larger than 0 when you're talking about calculus concepts. So we want numbers just a little bit bigger than 0. That's going to be the middle piece, because these are just bigger than 0 but smaller than 2. So we're going to use 2 minus x for that one. That is also a polynomial and eligible for direct substitution. So that limit is equal to 2, which tells me that the limit as x approaches 0 overall on this function does not exist. So what does that tell us about continuity? Well, the limit doesn't exist. So what kind of discontinuity is that? That's a jump discontinuity. So we have a jump discontinuity at x equals 0. And then the next question is, at 0, is it continuous from the left, from the right, or neither? If you want to check if it's continuous from the left at 0, you have to compare the left-hand limit at 0 to f of 0. That's these two. Are they the same? And the answer is yes. So this one is continuous from the left at 0. Once we know it's continuous from the left, you can check if it's continuous from the right by comparing the right-hand limit at 0 to f of 0, but they are definitely going to be different. Ask yourself this question. If you know a function has a discontinuity at, say, 0, is it possible for it to be continuous from both the left and the right at 0? Think about it for a second. The answer should be no. If this is continuous from both the left and the right, it's continuous overall, which means you don't have a discontinuity at 0. So once we identified that it was continuous from the left at x equals 0, there was no way it was going to be continuous from the right as well. So that is 0. We now need to examine x equals 2 in the same way. So for x equals 2, we want to look at f of 2. So in which piece are we allowed to plug in 2? The answer is none, because the middle piece is for x strictly smaller than 2. The bottom piece is for x strictly larger than 2. So f of 2 in this case is undefined, which means we are definitely going to have a discontinuity there. Let's figure out which kind and whether it's continuous from the left, right, or neither. So we look at the limit as x approaches 2 from the left on the function. As x approaches 2 from the left, you're coming at 2 from numbers slightly smaller than 2. Slightly smaller than 2 is going to be the 2 minus x piece. So the limit as x approaches 2 from the left on 2 minus x, that is a polynomial and therefore is eligible for direct substitution. So that's 0. We then need the limit as x approaches 2 from the right on the function. And from the right side, you're coming at 2 from numbers slightly larger than 2. That's going to be the bottom piece. So we get the limit as x approaches 2 from the right on x minus 2 squared. Also a polynomial. When we do direct substitution, we get 2 minus 2 for 0, and 0 squared also gets me 0. So this limit does exist as x approaches 2. The limit as x approaches 2 on this function is equal to 0. So what kind of discontinuity does that mean that we have? That's a removable discontinuity. If we then want to determine if it's continuous from the left or the right or neither, we need to do some comparisons. To determine if it's continuous from the left, at 2, we compare the left-hand limit to f of 2. Notice they don't match. So therefore, it's not continuous from the left at 2. And if we want to determine if it's continuous from the right at 2, we compare the right-hand limit at 2 to f of 2. Also, it doesn't match. So this is neither continuous from the left or right at x equals 2. If you look at a quick rough graph of what this piecewise function looks like, all of these discontinuities should make sense. Let's do it. Let me do a really quick and rough graph of this. If you look at the piecewise function, the first piece occurs only when x is less than or equal to 0. So that's on the left side of the y-axis. And what it looks like is a basic shape parabola, x squared, plus 1, meaning it's vertically shifted up by 1. So here is your 1, and it only exists on the left side, so it's here, and it's a closed circle at 0. The second piece only exists between 0 and 2, and it's a line. Specifically, this is negative x plus 2 if you want to write it in the more traditional form. So this is a line with a y-intercept of 2 and a slope of negative 1. So it has a y-intercept of 2, open circle, and a slope of negative 1. So as it moves down 1, it moves right 1, and down 1, and right 1. Open circle here as well, and that's a line from here to here. And then the last piece only exists if x is greater than 2. So to the right of 2, that is also a parabola because it's the x squared, but because the minus 2 is inside the function, that's a right shift. So this is a basic shape parabola shifted to the right by 2. So notice that's going to put your vertex right here. And there's your basic shape parabola. This is rough, but this is a general idea. But this is still an open circle. So it's not a surprise if you look at the graph. As you come in from the left versus if you come into the right. There's your jump discontinuity at x equals 0. And here's your removable discontinuity at x equals 2. So feel free to verify these graphically. That's not a bad thing to do. But you want to know how to determine the continuity of these algebraically as well. So why are we looking so hard at continuity? One of the other reasons we do this has to do with the calculation of more complicated limits. So let's take a look at a couple more quick theorems and see how that's going to help us when we go to calculate some limits. So the first theorem we want to look at says, if f and g are continuous at a, so there's the requirement of continuity there, and c is a constant, then the following functions are also continuous at a. F plus g, f minus g, a constant times the function, the product of the two functions, and the quotient of the two functions under the assumption that your denominator is not going to be 0 when you plug a in. So why is that helpful? Well, let's say you have a relatively complicated function and you're able to determine the continuity of the pieces individually. So let's say I've got these two functions being added together, but I can tell pretty quickly that f, let's say it's continuous everywhere as long as you're not looking at 3. It's continuous everywhere at 3, meaning it has a discontinuity at 3. And g, it's continuous as long as your x values are non-negative, so greater than or equal to 0. Well, then the sum of those two functions is going to be continuous for all positive numbers except 3. So they'd be continuous on 0 to 3 union 3 to infinity. So this is set builder notation. This is interval notation. So rather than having to add the two functions together and then determine the continuity, you can instead just determine the continuity of each piece individually and then combine those together. It makes it a little bit simpler. And that's also true for the differences, the products, the quotients, and constant multiples. So that's the first theorem we have. Let's take a look at another one. This theorem has to do with the composite of functions. And remember, while numbers have 4 operations, numbers have addition, subtraction, multiplication, and division. Functions have 5 operations. They have addition, subtraction, multiplication, division, but they also have composition, meaning to put one function inside another function. This theorem says, if g is continuous at a, and f is continuous at g of a, then the composite function f compose g, which is f compose g of x, or f of g of x, is also continuous at a. So the thing to keep an eye on is that g, based on this theorem, is considered your inside function. So in other words, if your g function is continuous at a, and your function f is continuous at its output, g of a, then the composition is considered to be continuous at a. Okay, so that's for composition. The other theorem we're going to kind of combine this with is that the following types of functions are continuous at every number in their domain. There's that continuity and domain link again. Polynomials, rational functions, root functions, and trigonometric functions. Okay. And before we discuss why this is important, let's remind ourselves of what the domains of these functions are. Polynomial functions, domain is all real numbers. We love polynomials, they've got great domains. Rational functions aren't too bad. They also have a domain of all real numbers as long as the number doesn't make the denominator equal to 0. Those are the only numbers you need to take out. Root functions, it's a little bit more complicated. If you want the domain of a root function, it depends on the index of the function. So by index, we mean this little n right here. So for example, if there's no n written there, if there's no number, if you see something like this, we know that that's the square root of x. Your n, your index, is 2, as opposed to something like the cube root of x. Okay, those are going to have different domains. If you have an odd index, meaning you're looking at more of a cube root, the domain is the same as the domain of the radicand. The radicand is what's under the radical. So in other words, if you just have, for example, the cube root of x, the domain of x is all real numbers. The domain of cube root of x is also all real numbers. If you have an even index, though, now you got to start worrying about taking square roots of negative numbers or fourth roots of negative numbers. And at that point, you just introduced imaginary numbers into calculus. And we want to avoid those like the plague for at least a little while. They eventually come up. But for this course, we're going to avoid calculus with I. So the domain for a root function with an even index is going to be all real numbers that keep your radicand, what's under your radical, positive. And then the domain of trig functions depends on which ones you're looking at. The domain of a trig function is going to be all real numbers that don't make your denominator equal to 0. So if you're dealing with something like f of x equals sine x, that it doesn't have a denominator other than 1, so its domain is all real numbers. As opposed to, let's say, f of x equals cosecant x, which, if you remember, that is 1 over sine x. That does have a denominator that has the possibility of being equal to 0. So the domain of cosecant x is all real numbers that don't make sine x equal to 0. So how is this supposed to help us when we're going to calculate limits? Remember the definition of continuity. A function f is continuous at a number a if the limit as x approaches a on f of x equals f of a. So in other words, if you know that a function is continuous, then you know that the limit as x approaches a on the function is the same as plugging a into the function. That should sound a little bit familiar. We did that some in the last section with polynomials and with rational functions. But what the definition of continuity says is that all functions that are continuous at a specific number, you can calculate their limits in this way. Well, what did we just say about these functions? they are continuous at every number in their domain. So if you want to calculate a limit as x approaches a that involves any of these functions, or their sums, their differences, their products, their quotients, as long as it doesn't make your denominator 0, then all you have to do is plug in a in place of x. So in other words, the limit of a function at a number a is the function with a plugged in other words f of a, as long as the function is continuous there. Again, with the assumption that you're not making a denominator equal to 0. So in other words, if you can plug in a to find the limit, assuming you don't get an indeterminate form or a 0 in a denominator, you should plug in a to find the limit. So when we look at an example like this, evaluate the limit as x approaches 9 of the square root of x divided by x plus 1. Technically, in the last section, you couldn't plug in 9 because this is not a rational function because of the fact that your numerator has a radical in it. This is not a rational function. It's close, but it's not. But now with these new limits and these new ideas of continuity, we know that because this is not going to give us a 0 in our denominator, all we have to do is plug in 9 everywhere we see x. So it's the square root of 9 over 9 plus 1. In other words, this limit is exactly equal to 3/10. If you want to look at the limit as x approaches pi on sine x over 2 plus cosine x, pi is in the domain of both sine x and cosine x, and it's not going to give me a 0 in my denominator, so I can just plug it in. I'll have the sine of pi divided by 2 plus the cosine of pi. What is the sine of pi? It's 0. What is the cosine of pi? It's -1. So that's 0 divided by 1, also known as 0. That is a much easier way to calculate limits than many of the methods we've already discussed. Something else we want to discuss is the Intermediate Value Theorem. The Intermediate Value Theorem says the following. Suppose that f is continuous on the closed interval ab. Closed just means we have brackets on the a and the b. And let capital N be any number between f of a and f of b, where f of a does not equal f of b. Then there exists a number c in the open interval from a to b. Open just means we're using parentheses, such that f of c equals capital N. That may need a little extra explanation. So let's start with the setup. Start with the requirements. We're required to have a continuous function. If you do not have a continuous function, the intermediate value theorem may or may not apply. We don't know. And it's only got to be continuous on the interval from a to b. When you see the word interval, a and b now represent your independent variable, which if you're talking about x's and y's is going to be x. So a is an x value, b is an x value. Notice this function is continuous on that interval. Let n be any number in between f of a and f of b. Well, if a and b are x values, then f of a and f of b are both y values. So those are your y values. This one over here is going to be f of a, and this one over here is going to be f of b. Those are your y values. Now we are required to have f of a not equal to f of b. They can't be the same y value for this theorem to work. Okay, once we have that all set up, n is any number in between f of a and f of b. They happen to have picked this n value, but this will work for any n value in between these two y values, which tells you that n is a y value. What the intermediate value theorem guarantees us is that there is a c value. It's an x value, but we call it c, somewhere in between a and b, where the y value associated with that c is going to be equal to that n. Let's take a look at an example. Prove that the equation sine of x equals 0.3 has at least one solution. Okay? Whenever you're trying to prove that an equation has a solution, intermediate value theorem is usually a good choice for that. We need to first make sure that we can apply the intermediate value theorem. Remember, the first requirement is continuity. The function f of x equals sine x is continuous everywhere. It's continuous on its domain, and its domain is all real numbers. So we can use any x values we want. What should we choose? IVT, Intermediate Value Theorem, talks about that a and that b. Right? We want to know what should we be using for the a value, what should we be using for the b value, and that was not expressly listed in this question. So how are we supposed to know what to choose? Well, what we need are two x values, because remember a and b are x values, that we can plug into the function sine x that will give us a number above 0.3 and a number below 0.3. If you kind of want to relate this to the graph we were looking at, 0.3 is going to be that end value. So we want to find numbers above and below. So what x values can we plug into a sine function that give us a number below 0.3? And what numbers can we plug into a sine function that give us numbers above 0.3? Now there are lots of correct answers to this. So I chose two numbers that are not necessarily going to be the ones that you chose. I chose the sine of 0 because the sine of 0 gives me 0. That's my number below 0.3. So this is one of my x values. And I also chose the sine of pi over 2 because at pi over 2 the sine function is equal to 1. That will give me a y value above 0.3. So in the intermediate value theorem, 0 is my a, pi over 2 is my b. A will always be the smaller one, b will always be the bigger one. And what I wanted were these two y values to be one above and one below 0.3. So that's why I'm going to choose 0 to pi over 2. You did not have to choose the same two numbers I did, and yet you will still be able to successfully answer this question. So what does this allow me to conclude by intermediate value theorem? Well, since I have a y value that is below 0.3, this is the 0, and I have a y value above 0.3, this was my 1, then what I know is that there exists a number somewhere in between 0 and pi over 2. So somewhere between 0 and pi over 2, such that the sine of x equals 0.3. Graphically, what that will look like, my scale's going to be off on this, but graphically, it means, you remember what your sine function looks like? It looks like this. You're going to cross this line, which is y equals 0.3. Notice that intermediate value theorem tells us that there exists a number that is going to make this equation true somewhere between 0 and pi over 2. It does not, however, tell us what that number is. And that concludes our discussion of continuity.